Hello. Today we are going to talk about regression modeling. More specifically, I'd like to provide an introduction to correlation analysis, start with discussion of what linear relationships are and what are the basics of the regression modeling. And then we are going to finish with discussing different types of the variables or the data items that are usually available as part of the research or analytic projects. All of these are going to set the stage for the next topics that are going to discuss as we move on. Let's start with the correlations. What correlations are, they help us to explain relationships between two variables or the concepts at a time. What they do, they measure the relative strength of the linear relationship between two different variables. And in other words, they are going to explain how the value of one variable changes in relation to changes in other variables. They usually range between -1 and +1, and they can take on any values between this particular range. They are strictly restricted to two variables at a time. In other words, we cannot measure three variables. And they are measured by the Pearson's correlation coefficient. Again, this is the coefficient that has been used in the textbooks and so on. So some of the examples why would we want to measure this type of relationships? For example, we might want to try to see if there is any association between gender and smoking, or level of education and smoking, wealth and obesity, for example, or race and obesity, right? As you can see, these are two variables at a time. We are trying to understand whether or not these two variables are correlated with each other and so on. Just remember, the correlation doesn't indicate causality, okay? The only it says is that there looks like there is a high level of relationship. The correlation coefficient, as I mentioned, it ranges between -1 and 1, so they can be positive correlations as well as negative correlations. The positive correlations are when the variables change at the same direction. For example, when we look into our income and the spending, right? As our income goes up, our spending will go up as well. So hence, there will be a positive correlation, or at least we'll assume that there will be a positive correlation. In the negative correlation, two variables move to opposite directions, right? For example, the same income and then spending on fast food restaurants, right? We would assume that as our income goes up, our spending in fast food restaurants will tend to go down by substituting our spending towards other type of restaurants. The coefficient, the Pearson's correlation coefficient is denoted with the letter R. So this is what you'll see in most of the textbooks or articles that you'll find online and so on. This slide provides a graphical illustration of the coefficients. You'll see on the upper left that this is where the coefficient is equal to 1. You can see it's an upward trend signifying a positive correlation. As one variable increases, you can go from left to right, you'll see that the other variable is going to increase, going from the bottom to the top. And this is a perfect correlation, perfect positive correlation, because you can see all the observations are lined up on the same line. On the top right panel, we have, again, a perfectly perfect correlation. However, it's -1, indicating that there is a negative correlation. As you can see, let's say the horizontal variable goes from left to the right. In other words, it's increasing. You can see how it is causing the other variable to start to decline, right? Again, you move from here to here, then you'll be able to see that one grows, the other one goes down. Then on the left panel, we have correlations that are not lined up on a strict line. On the left-hand side, we have a correlation coefficient where it is equal to 0, which basically means that there is no correlation. In other words, the variables or the data, two variables, are moving in a random pattern. They are not correlated one to another one. On the right-hand side, we have a correlation that is not 0, it's not 1, it's not a positive, perfect correlation. However, it is positive and it can take on any value between 0 and 1, given a specific case. So in this case, you can see one variable or one observation or data point is located on the linear line. However, the rest are scattered around it. That for that reason, we don't have a perfect correlation. In this slide, this particular slide indicates the different types of the correlations and a relationship, again, summarizing what I have just mentioned. How does the X and the Y, for example, relate to each other? And in terms of the coefficients, how do different types of ranges get interpreted? The direction of association, again, as mentioned, there are positive and negative ones. You can see on the left-hand side, it is a positive correlation. It's like upward growing. As X grows, Y grows with it. And then the other one is a negative correlation, where a growth in one causes the other one to decline. And this is an example of an actual calculated correlation coefficient, just to show how the graph or the scatter plot will look like for different types of value. On the left-hand side, top and bottom, we have the perfect correlations where the coefficient is equal to either negative or positive one. And as you can see, they are very much lined up on the same line. On the right-hand side, the far right, we have the correlation coefficient of 0, indicating that a change in one variable doesn't cause a change in the other variable. And then finally, in the middle one, we have correlation of different degrees. For example, at the top, we have a negative correlation because as X increases, Y is going to go down. And then on the bottom one, we have a positive correlation, however, very smaller now correlation, where as X grows, Y is also going to grow, as you can see from the fitted line. How to make an interpretation of the correlation coefficients? Again, it's very arbitrary. In other words, there is no specific rule. However, there are some kind of rule of thumb. Okay, when we think about a very strong relationship, so this is where the coefficient is between 0.8 and 1.0 in absolute terms. It can be negative 0.8 to negative 1. The strong relationship will be between 0.6 and 0.8, plus or minus. Moderate relationship, 0.4, 0.6. Again, this is something around like 0.5. Then you have the weak or no relationship, which is basically a lower number, either positive or negative. So these are the basics about a correlation. Again, this is something that you will see a lot in statistics or other type of data analysis. This is something to get started, where our intention is to try to understand whether or not two variables are correlated to each other or not. And it will become more obvious of why would we want to look into this type of relationships when we start our data analysis in the next weeks. Okay. Finally, you can calculate correlations on hand. If you have a small data set, you can do it in Excel, or we can do it in Stata. Stata is the software that we are going to use to conduct our analysis. And there's a syntax or a command in Stata that will help us to calculate very quickly within a matter of less than a second. And I'll talk more about this command when I provide an introduction to Stata and we start to actually looking into some of the examples. Just an overview, the correlate command in Stata provides a correlation or calculates the correlation coefficient for two different variables. Here we can even specify a large number of lists in terms of the variables. However, the calculations are going to be done for two variables at a time. Okay, so that wraps up the very basic introduction to correlations. And as we move on through the topics, then we'll be able to do some actual examples and try to incorporate correlation analysis into our broader analysis of the data or the problems that we are trying to address. Okay, so now let's focus on the linear relationship. Again, you can think about the linear relationships as the topics that have been covered in the algebra classes. Okay, well, the intent of the next couple of minutes is to provide you an overview of what a linear relationship is. Examples of linear relationships are a lot. So I'm pretty sure as I move through some of these examples, you'll be able to relate to some of the examples that you have seen in other classes that you have taken. For example, on this graph, we have the X and Y coordinates axis, right? On the X, which is the horizontal, we have the number of games that have been rented, right? We have 5, 10, 15, 20, 25. Then on the vertical, our Y-axis, we have the total cost of the rental. As you can see, if you rent 5 games, it's going to cost you about $30. If you rent 10 games, it's going to cost you about 40 bucks. 15 games, about 50. 20 is $60. 25 is approximately $70, and so on. As you can see, the starting point when you rent 0 games, it's still $20, which may indicate that perhaps you need to have a subscription fee, after which you'll be allowed to pay to rent per fee. Okay, so as you can see, once we plot these relationships and then try to connect the lines, it's a straight line. So hence the name linear relationship. Or this one that looks into the relationship between a time, for example, spent in doing something, and the cost of it. This, you can think about this as your wage rate, right? If you work X number of minutes, then this is how much you are going to earn. Or if you utilize a particular service, let's say per minute, this is how much it is going to cost. And then we try to plot it on an X and Y axis, and we are able to see that all these 4 points are able to be connected using a straight line. Again, the key in this relationship that we are talking about is that these lines are being connected with a straight line. Or here, where we look into the time and the amount of the water that has been leaking from the faucet. Okay, again, given that it is leaking at a constant rate, then the relationship will be able to represent as a straight line. And finally, this is also something that all of us will be able to relate, the relationship between the degrees of Celsius and the degrees in Fahrenheit. Okay, again here we have a linear relationship that is provided by a particular formula where we are able to convert the Fahrenheit into Celsius. So all of these are the types of the graphs that perhaps we have seen in one form or another in the past in other courses. So these are the ones that are helping us to provide a kind of an overview of what a linear relationship is. Let's look into doing like illustration. Think about this one. We go out for a pizza, right? And then we have the choices to order, let's say by slices, right? So if we order 0 slices, again, on the left-hand side of the table, we have the number of slices that one might order. On the right-hand side is the price if you order that many slices. For example, if we order 0 slices, then it will cost us $0. If you order 1 slice, then it's $5. If we order 2 slices, then it's $10. And so on. If we order 6 slices, then it will cost us $30. As you can see, the difference in the number of slices is $1. It's 1 unit, a single slide every single time we are increasing. On the right-hand side, we also have the incremental change is $5, right? Basically indicating that per slice cost is $5. Then when we try to graph these data points, right? In other words, 0 slices, $0. 1 slice, $5, 2 slices, $10, and so on, then we'll be able to get the following. So this point right over here, you can see the red dot, is the coordinate or the data point for 0 slices that cost $0. The next one is 1 slice, $5, 2 slices, $10, 3 slices, $15, and so on, all the way until 6 slices and $30. So if we try to connect these dots using a straight line, we are able to see that we can easily connect them without any issue. We don't need to bend the line. It is a straight line. The reason it is a straight line is because the incremental change or the marginal difference is constant. In other words, when you move from when we add additional slices, the cost or the purchase is changing by the same amount. Therefore, we have a straight line. Okay, so again, this is one of the kind of the fundamentals of the straight lines where our incremental change is identical. Okay. Usually, linear relationships are represented by different multiple parameters. We start with the equation form. You can see on this slide that we have y. Well, we have the y-axis on the vertical and then x-axis on the horizontal, right? Again, trying to recall our algebra. In this case, the straight line can be represented as y equals mx plus b. Okay, this is the general form of a linear relationship. And now we'll try to look into what different letters indicate in this particular relationship. To start with, let's say if we have two data points, both of them have their own coordinates. In other words, they have their value of x and the value of y. So in this case, this will be the value of x, and this will be the value of y. Okay, so we have So we have the value of x, and then we have the value of y. The same thing for the other one. We have the value of y for a particular value of x. So each data point has its own unique x and y values. Okay. So here you can see that the different parameters that characterize a particular linear equation are the intercept, which is right over here, and its slope. Okay, let's look into them in more detail. Okay, as I mentioned, the standard form for a linear relationship is y equals mx plus b. In this case, you can substitute the letters for depending which ones you want to use. The overall relationship doesn't change. Okay. So the only thing to keep in mind is that here we have the freestanding term, in this case the b, which is not connected to the x. Okay, in other words, this is the constant. And then we have the second part, which is the part that varies based on the value of x. If x is a 0, then m times n, and m here is a constant as well. So if x is 0, then any number times 0 is a 0. If x is a 1, then m times 1 is a m. If x is 2, then m times 2 is 2m, and so on and so on. Okay, so the second one is the slope. So basically, b in this case would become our intercept. Then we have the slope, which is basically defining us how much does the value of y change for a change in x. Hence, y2 minus y1 divided by x2 minus x1, or also change in y divided by change in x. For example, if we change x or increase x by 1 unit, how much will our y change? And this is the one of the most important components of, for researchers, because we are interested in these relationships, right? Think about this. If we are talking about the taxation, for example, right, or the price of the cigarettes and how much people consume cigarettes. And we do know that by a theory, if we raise the price of the cigarette, then the consumption will go down. So as a public health service, we are interested in lowering the consumption of the cigarettes. Therefore, a question for a researcher would be, well, if I increase the price of a cigarette by $1, how much will the consumption of cigarettes drop, right? So these are the types of the questions that we are interested in. And by looking into, if we model that price of a cigarette versus consumption of a cigarette as a linear relationship, then we are able to look into the slope, which is again change in y given change in x, and try to determine what's the policy effectiveness, or what is the effectiveness of a change in the pricing. Again, to start with, to reiterate the intercept, this is the parameter that indicates where the linear relationship crosses the vertical axis. This is the status quo. Okay, the intercept is always a constant. It doesn't depend on the level of the x. In this particular equation, right over here, b becomes our intercept because it is freestanding. It's in a freestanding form. It is not associated with an x. And that's usually, you'll find it's right over here where the linear line or the equation intersects with the y-axis. It can be above 0, which is right over here, or in some cases, depends how it is, we might have a line that intersects y-axis at a negative point, let's say -1. Okay. The next one is the slope. Again, as I mentioned a minute ago, it indicates the change. How much will our y variable or one variable change given a change in the other variable. Graphically illustrated is basically is going to talk about this. We are talking about the slope of the curve if we are looking at it as a triangle. Another concept that is very much used in applied research or analytic projects, no matter in which field you are working, public health, economics, finance, and so on, is a notion called elasticity. Elasticity uses the slope and converts into a percentage change, okay? Because when we talk about being able to provide a meaningful interpretation of our results, for the general public, it is much easier to understand concepts when we talk in terms of the percentage changes. For example, if we change the price of a cigarette by 1%, how many percentage points of a drop in consumption can we expect, right? So many people do relate to the ideas if we express them in a percentage terms better than in other form. Therefore, as a researcher, as an analyst, for us, calculating the elasticities is a way of expressing the results in a more meaningful and easier to understand way. Again, the elasticity is the percentage change in one variable associated with a 1% change in another variable. In terms of the calculation, it is denoted with a letter epsilon. Okay, basically elasticity of y with respect to x. Again, it's the percentage change in y given a percentage change in x. And then when we calculate the slope, and then we multiply it by the ratio of x to y, we obtain the elasticity of a particular variable with respect to the other variable. This is just meant to be a very brief introduction of the concept of elasticity. As we move on with the analysis, we'll talk more about the elasticities and how they are derived from our analysis. Okay, so hopefully until now you are able to refresh your memory and your knowledge of correlations as well as what are linear relationships. And from now on, we are going to move into the core of our course, which is try to perform quantitative analysis of the data that we have by utilizing regression analysis. So in this presentation, I'll try to also provide a very brief outline of what is a regression analysis. I'm not going to go into many details or try to provide examples, hands-on examples, because that's the purpose of the next presentation. In this one, I'll basically talk about what regression analysis is, what are the foundations of it, and why do we need to use them as part of our research. So in a simpler term, linear regression, which is one of the basic forms of the regression analysis and used widely, is predicting the value of y based on some value of x, right? So again, we are trying to understand what will be the value of one variable when the value of the other variable has a particular value. Okay, assuming that there is a relationship between these two variables. So the purpose of regression analysis and what we are going to learn in this course is to try to properly understand, first of all, whether or not there is a linear relationship between the variables. And if yes, then what is the strength of the relationship? In other words, how can we predict a value of y when the value of x changes? You can also see, in this sentence, I'm using two terms, dependent variable and independent variable. From our previous discussion, I've already introduced you to the concept of dependent variable and independent variable. Remember, dependent variable is the variable that is changing depending upon the value of another variable. And the independent variable is the one that causes the change, okay? So throughout this course, we are going to use these two terms constantly. And even though from the previous presentation we have learned that there are many other forms of referring to these ones, however, the notion itself doesn't change. Let's take a look at our earlier example, where we are looking into how does the price of a purchase change as we change our ordering of this number of slices of the pizza. What we looked into is that the relationship is represented as a linear or straight line, right, as you can see on the graph. So when we think about, okay, so given that, how can we put this in a form of a linear equation, right? So our general form of a linear relationship or linear equation is y equals mx plus b. Well, in this case, we have the value of y, we have the value of x, right? Those are right over here. This is the x and this is the y. Now we need to try to understand what is the value of m and what is the value of b, right? Remember, b is the value where the line, our straight line, intersects with the y-axis, right? In other words, this is the value when our value of x is equal to 0. We can see from the table that when our x, or number of pizza slices, is 0, then y is equal to 0 as well. Therefore, we already know the value of b is equal to 0 right over here. And then we also know that incremental change between x and y is $5, right? And that's where our m is. In other words, m is indicating how much the value of y is going to change for every single extra unit change in our x. And hence we have our linear equation expressed as y equals to 5 times x plus 0. So why is this important? Well, if we want to do predictions, right? For example, if we try to understand, well, how much will 10 slices of pizza cost, right? Well, if we plug in 10 instead of x, right? 5 times 10 is 50, plus 0 is 50. Therefore, if we purchase 10 slices of pizza, it is going to cost us $50, right? So this is, again, a very simple way of trying to illustration why predictions are useful. In a real life, of course, we have more than 6 data points. It is more complex. But however, we still are trying to provide predictions. Again, for example, if I raise the price of a cigarette by another $1, how much will it change the consumption of the cigarette? These are public policy issues that are relevant for researchers as well as decision makers. Okay. In a more complex situation where we have thousands and tens of thousands of data points to look through, of course, doing all of these calculations by hand becomes very challenging and very time-consuming. Therefore, we use software and computing technology to perform all of these. And we'll see as time goes on how to do all of this. Again, for today's presentation, I'm primarily focusing on laying the foundation of different concepts that will be used as we move on. Let's look into another example. Here too, we have data points. We have the x and the y, and then when we try to, you can see them from the table. Then when you try to plot them on a graph, then we have 1, 2, 3, 4, and 5 data points, right? As you can see from this graph, then it's impossible to draw a straight line through every single point, right? If we draw lines for this point, right, then it's going to omit actually all 3 points. If we try to draw a line from all points, right, then it is pretty much becomes a zigzag, right? So it's not a straight line, okay? So the question becomes, and in reality, data points are not always a straight line, right? The relationships are not expressed as a straight line by default. So in reality, our data looks like more like scattered around a straight line, right? If we were to think about this one, let's see if I can erase this. Okay, so in reality, our data points are scattered around a straight line rather than being on a straight line. For example, they can be something like this, right? So they are kind of nearby the straight line, not necessarily all of them. Maybe 1 or 2 might be on a straight line, but not all 5 of them, okay? So the objective of the regression analysis is to, when we take our data that we observed on X and Y, is to be able to fit a straight line through these data points. This fitted straight line will not necessarily go through every single line or even the majority of the lines, okay? However, the objective becomes is how can we position this a straight line through these data points that will be able to describe the relationship between x and y with as high possible possibility of accuracy as possible. So this is what we'll be doing throughout the entire course of this class, is trying to understand what our data looks like and how can we fit the straight line. Again, fit a line is kind of a terminology that you'll see more and more as you are reading and as we are moving forward with these classes that I'll be using. Let's look into that same example. Okay, so the black line on this graph is what our predicted or fitted line is. Okay, and this is the straight line which will be given by its own equation, y equals mx plus b. Okay, even though it doesn't go through every single point or even any of the points. However, this predicted straight line or prediction line allows us to summarize the relationship between x and y. Then we have the color points, which ones are actual data. As you can see, for example, the purple one over here, right? So this is where the actual data is located. However, its predicted value is located right over here. Okay. Again, we have the x value of 5. Its actual value of y is 2.25. However, the predicted value of y is approximately 2.8, right? Okay, and that's what causes our next term, which is called the errors of the prediction. And again, the errors of predictions are basically the difference between the actual value, right, 2.25, right, and the predicted value of 2.8. In this case, you will have approximately 0.55 of an error. Okay. In regression analysis, errors are an integral component of the analysis. Our intent is to try to get our errors as small as possible. However, we can never get it to 0. Okay, simply because unless, of course, all these 5 lines, the colored lines, are located on a straight line. In that case, of course, the error becomes 0. But when they are deviate from being on a straight line, then in this case, we are going to have our prediction errors, which again is very common in regression analysis and is an integral part of it. Okay. So again, we talked about these prediction lines, right? In the previous example, we saw that, well, the black line that is fitted there is the one that characterizes the relationship between x and y, right? So does this green line. However, if I were to ask you to draw lines through these points that will provide some sort of a kind of a summary of the relationship, then you might draw it like this or like that, or maybe like the blue line, or even as the other black line, right? So as you can see that there are different ways of drawing a straight line through these data points, right? So the question becomes for a researcher, well, which one is the best line? Because depending which line you pick, right, you can see that their intercepts or the constant or starting points are different. Their slopes are different. Therefore, in the straight line equation or linear equation of mx plus b, both m and b are going to be different, and hence our predictions are going to be different. So the question becomes, well, which one should we pick, or how do we draw this line, fit the line that is the best, so-called, right? So when we conduct regression analysis, when we analyze our data in a regression model, then it helps us to determine which one of these lines fits the data the best, okay? And that's what we are going to learn, how to conduct the analysis given our data points to actually discover the so-called the best line. How? Well, we are going to learn in the next iterations of the course or in the next weeks. But for now, I just wanted to give you just a simple preview of what we are trying to accomplish, and what is the purpose of the regression analysis. Let's take an example. I'll provide two examples. The first one focuses on the SAT and college GPA. In other words, we are trying to understand, well, what's the relationship between an SAT score and the college GPA that any student will have. This is the data that is taken from 105 students who graduated from a state university with a BS degree, Bachelor of Science degree in computer science. Our research question is how we could predict a student's university GPA if we knew his or her high school GPA, right? Think about this. If you are a school administrator or an advisor to a student, right, then we want to identify the students who are likely to have low university GPA so that we can intervene early on and provide some counseling and so on. Okay? And the data set is located at this website. You can actually go there and take a look at it as well. So when we try to plot the data, all 105 points, right? So this is what it's going to look like, right? So on the horizontal axis, we have the high school GPA. On the vertical axis, we have our dependent variable, our university GPA. What we are trying to understand is, well, how are these related and how can we express this relationship as a linear relationship so that we can make predictions, okay? So again, what we are trying to do is basically fit a line for this data point. Maybe the line looks like this one, okay? Or maybe the green one, or as a yellow, or as the purple line, right? So again, our purpose is to try to understand how do we analyze the data to identify the best line. One of these four is the best one, right? So our objective will be to identify the best line so that we are able to properly make predictions for the future. Okay. Another example. This focuses around our income and how much we spend on food, for example. Okay. Let's see. We have 40 households, and we have data on how much money they spend on a week, on food, and then what's their weekly income. In this case, it's in 100. So basically, 3.69 is 369. 4.39 is like 439. It's just the way data is coded. Okay. So why is this important? Well, what we are interested in is trying to understand how the spending on food changes when a household gets a particular level of income. Okay. Let's say if we expect that in a neighborhood our households are going to experience a growth in their income, then if you are a neighborhood grocery owner, then that gives you an indication. You want to understand how much more business you might get, right? If these households are going to experience higher incomes, hence it is going to increase their food expenditures, then you need to actually think about, well, should I expand my grocery store? Should I expand the offering of grocery items, and so on? So again, from a policy perspective, from a research perspective, these are important things to look into, okay? When plotting the data, and I'll talk this example in more detail in the coming weeks, but today I'm just going to provide you just a brief overview of the data and where does this fit within the concept of the regression analysis. So when we plot this data, then this is what we get, right? On the horizontal axis, we have weekly income, and then on the vertical axis, we have weekly food expenditures. Again, our purpose is to try to feed a straight line for these data points that summarizes the relationship in the best possible way. And again, as I mentioned, we will learn what is the best later on, right? In the next week when I talk about the simple linear regression. So once we are able to identify what's the line, in other words, the line parameters, in other words, its value of B, then its value of M, now we are able to make predictions, okay? For example, you can think about, okay, so what if a household had an income of 1,960? Remember, income is multiplied by 100, okay? So if a household's income is 1,960 per week, then how much are they going to spend on food, right? Well, we can plug in, right over here, instead of an X, it will be 19.60 times 10.21 plus 83.42, and that will give us a new value or predicted value of the household food expenditures. Okay, So that's the reason that we need to calculate what is the value of b, right? Then what is the value of m in this linear relationship. Okay, in a more technical form, the regression equation is written as y equals beta 0 plus beta 1 multiplied by 10 by x and plus the error term. Remember, in a linear relationship on a straight line, right, if all the data points are located on the straight line, then the error is 0, so there is no error there, right? However, in the real world, when we deal with real world data, it is almost impossible to have all the points lined up on a straight line, right? So for example, take this point, right? There's this error right over here. Its original value and then predictive value. And then we have this one, right? Even larger error. Or this one, a tiny one. Well, this one almost doesn't have any errors. This one has, for example, that much of error, right? So we have all of this one, and this one is almost located on the line, and so on, right? So error needs to be part of it, right? So here we are going to have our b from the previous notations. We have our m, okay, multiplied by x plus the error term. In this regression equation, and throughout the semester, we are going to focus on these equations. Y is our dependent variable, x is the independent variable. We have the beta 1, which is the intercept, the baseline, starting point, okay? Beta 0. Beta 1 is the regression coefficient that describes how y and x are related to each other, okay? Remember, that's our slope variable. And then finally, we have the error, or the error of the prediction. And for every regression model, we are able to calculate, well, what is the error, right? In this case, error will be the difference between that value and this value, okay? In reality, from this equation, x and y are observed, right? In the case of the food expenditure, x will be our income, while y will be how much money we spent. For example, if I were to survey the class, or I conduct a survey in a community asking people, well, what's your weekly income and how much do you spend on food? And they are going to provide these numbers, right? Assuming they don't refuse to answer the survey questions. So we have in reality the values of x and y. These are observed either in a real life, for example, we can look into the pay stubs and so on, or through some experiments like the surveys, where we ask people to reveal how much money they are making and how much they spend on the food on a weekly basis. From the other side, beta 0 and beta 1 are unknown. So our task as a researcher, as a individual who conducts regression analysis, is to actually estimate the value of beta 0 and the beta 1. Okay, once we estimate beta 0 and beta 1, then, and knowing what the value of y and x is, then we are able to conduct predictions with the data. Okay, let's take two more examples, more briefly, right? Let's say we are conducting our regression analysis, and we receive that we are looking into a relationship between the size of the house as measured by the square footage and the price of the house in the market, right? So we take the data that comes from the market, right? The house has its own square footage and how much it was last sold for, right? Or how much it is currently valued. Let's say we collect the values for 1,000 houses, and then we do estimate our beta 0 and beta 1, right? And we get a value of 15,000 and 1.25. In other words, the way house price changes is our beta 0 is 15,000 plus 1.25 multiplied by the square footage. Okay, so here what the 15,000 or beta 0 is, sometimes beta 0 in these equations has a specific meaning, sometimes it doesn't. It is necessary for mathematical reasons. In this particular case, it does have a meaning, because think about this. When the house price will equal to 15,000 only if square footage is equal to 0, right? In other words, there is no house on the land, right? Which basically reduces the house price to the price of the land. So 15,000, or our intercept, becomes the cost of the lot where the house is to be built, okay? And then we are also interested is, well, how much will the price of the house change based on the square footage, right? Well, let's say if the house has 1,000 square foot, uh, it's the house size is 1,000 square foot, then 1,000 times 1.25, right? That will be 1,250 plus 15,000, that will be 16,250. So that will become the price of the house. So as you can see, this type of data can be used by real estate developers to try to see, given a particular neighborhood, a particular lot, what kind of a house to build. Should we build a house that is 3,000 square foot, or should we build a house that is 2,000 square footage? Okay. Another example comes from the field of the healthcare medicine, right? Let's say we have a headache, right? One of the things is, well, let's take an Advil and try to see if that will help us to bring the pain level, right? So let's say that the pain is measured on a level of 0 to 1, okay? 10 being that we are in an extremely pain. And then we are going to use Advil, take an Advil, right? Try to reduce our pain level, right? So again, when we are taking 0 Advil, right? 0 times 2.5, then this expression becomes 0, so that our pain level is at the top. So as we are starting to take Advil, let's say 2 units, right? It's 2 times 2.5, it's 5. 10 minus 5 is 5, right? Meaning that our pain level went down by from 10 to 5 by taking 2 Advil, and so on and so on. And when you take 4 capsules of Advil, it will make the pain level to be 0. In other words, it goes well. So as you can see, again, from a pharma research perspective, we are interested in, okay, what are the different dosages of the medication that we are developing that are going to help to cure the underlying conditions. So again, I hope these examples provide you a good beginning understanding of where regression analysis is being used. Again, remember that we always observe, or we are able to identify what the value of x and y is, right? However, what we don't know is how they are related. What's the slope? What's the intercept? And we are going to use regression analysis to calculate these values. Okay. Okay, so with that said, I'm going to stop here in talking about regression equations and regression analysis, simply because as we move on throughout the semester, we're going to touch upon this topic more and more, and today's presentation solely aims to provide you with just a beginning understanding of what are the main concepts that we'll be using throughout the course. In the second part, what I want to do is I want to focus on what are the different types of the data that we will be encountering in our daily life or as part of our professional careers. Okay, so we'll start about how are the data generated. Okay. We in our life work with very complex data sets. Okay, look around yourself where you are working or where your career path is, and you'll be able to see that as part of your job, you are interacting with lots of data, directly or indirectly. Okay, so it is very important for us to have a really good understanding of what kind of a data we work with, because our analytic approach to that particular data is going to be different from another type of data. Okay, so data can be experimental and non-experimental. They can be cross-sectional, time series, as well as panel data or longitudinal data that is more familiar in some of the literature. Okay, so in the next couple of slides, I'll talk about what are their differences. Let's start with experimental data. Okay. So experimental data are the data where the values of key control variables are specified, and then we are observing the outcome. Take about agriculture, okay? So we are planting or we are providing the inputs, in this case, planting the seeds, providing the land, fertilizing, right, watering, right? Then we're going to wait and then at the harvest calculate the yield, right? So this is experimental because we're experimenting by applying different levels of seed, different types of fertilizer, and then observing how the yield changes based on that, okay? In the business world, in retail, right, we design a product, right? Then we package it, Sometimes we use different types of packaging. Then we might use different types of pricing strategies, right? So that's our experiment. And then we are going to wait and observe the results. In other words, okay, how many we sell and how much of a revenue we generate from this, okay? Or in a healthcare or public health, right? We might follow a cohort of people that are assigned into two different groups, right? The first one, right, might receive a different smoking cessation aids, okay? Or the other, then, for example, one can be a medication in terms of the smoking cessation aids. The other one can be a referral to the quit line. The other one can be behavioral therapy. Okay. So then, what we are interested in, well, try to understand how do these different types of cessation aids impact the outcome of smoking. In other words, in this case, the quitting behavior over time, right? So again, we're experimenting. We are choosing multiple inputs, in other words, types of the cessation aids, and then we are going to observe what the outcome is. In contrast, in non-experimental research, we don't have this observational piece in terms of we provide the inputs and then we try to observe and see what the data are, okay? Usually these are the so-called survey data where we are collecting the entire data simultaneously. If you recall again, in experimental, it's like stepwise process, right? First we are applying the inputs and then are waiting to try to see what the output will be. In the case of non-experimental data, which are primarily based on the survey data, we are collecting inputs and outputs at the exactly same time. Think about this. We are doing in-person, mail-in, phone, online, or mixed methods survey collection where we are calling someone and asking a whole bunch of questions, and we are collecting all of this data at exactly the same time. So these are the non-experimental data. The opinion polls are one. When we do a survey on the campuses asking about students' smoking behavior and their attitudes towards, for example, tobacco-free policies, well, this is a non-experimental design as well, okay? Or we provide testing, right? You might have encountered where you are asked to taste a product and then provide your attitude and preferences about that, right? So again, all of this information is collected at the same time. That's the major difference between experimental and non-experimental data, okay? In terms of the dimension, again, in terms of the experimental versus non-experimental, nobody is claiming one is better than the other one. It all depends on what's the context of your analysis. Sometimes you might deal with one type, sometimes the other one. At the end of the day, again, it's really just important to identify or realize where the data is coming from. Dimension-wise, data can be, or variables can be cross-section, time series, or panel or longitudinal. So in the next couple of minutes, I'll talk about each one of them so that you have a really good understanding. So the cross-sectional data is the data that is collected across sample units in a particular time period. It is collected once across multiple units. Again, think about a survey of the entire class or the students on the campus, right? We are conducting this survey one time and we are sampling from multiple individuals, right? As the example, on the example below, let's say 9 individuals, okay, were asked what their race was, what their level of education was, what's their marital status, what's their gender, how many hours do they work, and what's their hourly wage rate. Okay, so again, this is collected across sample units. In this case, an individual is the unit at a particular time period in a single point of time. We are not repeating this. Okay, so this becomes our cross-sectional data. Every single survey, unless they are repeated, where you contact the same person, let's say every year or every 5 years, asking the same set of questions. Unless that's the case, then we will be dealing with a cross-sectional data. Okay, the time series data, as the name suggests, is the data that is collected over time. Okay, think about, let's say, take a specific indicator, right? For example, the gross domestic product of a company, of a country, or let's say a revenue of the company, right? So if we are collecting the same data over and over and over time, let's say every year, every month, every quarter, right? So then we are generating time series data, and graphically you'll be able to see how time series data are depicted, right? You have the time on the horizontal axis, and then you have the GDP value on the vertical axis. Okay. Then this brings us to the final version, which is called panel data, or also known as longitudinal data. Basically, this is a combination of both cross-section and time series, where multiple micro units or sampling units are followed or sampled or surveyed over time or multiple times. Okay. For example, we have two firms, firm 1 and firm 2. And then we have multiple years, 1990 to 97, right? We ask each firm in each of these years questions about how much they produce, what was the land area they have used, how much of a labor they have used to produce the crop, and how much of fertilizer they have applied. Okay, so you can see we have the time dimension in terms of the years from 1990 to 97. And then also we have the sampling units, which are firm 1, firm 2, and then firm 3, and so on and so on. And this generates a panel data, or also in the health field called longitudinal data. Okay. One of the key components of the longitudinal data is that the firm 1 is the same every single year. Firm 2 is the same every single year. Okay. When we do a survey like this, then this generates a panel of the data, or longitudinal data. However, if we do the same survey, let's say a survey about how much people smoke, right? We do this every year, randomly selecting people on the campus. Then this is not a panel data, even though you might get the prevalence rate of the individuals for multiple years, but because we never tied these individuals together, okay, then it doesn't account as a panel data. Okay, so that's called a pooled data when we pool all the data together. Okay, the variables or data can also be qualitative and quantitative, and again, this is going to be very essential for the rest of the class. Okay, so please make sure you pay lots of attention. So let's start with the quantitative data. Okay, so the difference between quantitative and qualitative is the following. Quantitative data have a well-defined scale of measurement. For example, temperature is measured by Fahrenheit or Celsius. Distance is measured by a mile, kilometer, and so on. The pressure has its own unit of measurement. Income can be measured as, let's say, dollars per week, or how much euros do we earn per year, and so on. As you can see, each one of them has its own specific, well-defined scale of the measurement, right? Within quantitative data, there are multiple varieties. Okay, there are ones that are called discrete or count variables. Okay, and these are the variables that do not admit intermediate values between two specific numbers, and they are represented by a whole integer value. For example, you ask people, well, how many brothers do you have, right? Let's say you ask 5 friends, how many brothers do they have? The first one says 2, second one says 1, the other one says 0, 1, and then 3, right? As you can see, these are integers. And because of what we are measuring, in this case, number of brothers that the person has, you have to have a whole number. You cannot have a decimals there, right? Or a ratio, or not an integer, because we cannot say I have 1.5 brothers, right? Or how many patients did the physician see yesterday, right? Well, 0, 1, 2, and so on. Again, it has to be measured as an integer, a whole integer, because we cannot see 1.7 patients, for example. Okay, so when we deal with this type of a data, then they are called discrete or count variables. Okay, they're still quantitative. It's just they're different than some others that we'll see. The next one is called a continuous variable. Okay, continuous variable can take on values between any two numbers. Okay, there is no restriction of what kind of a value can it take. For example, in the case of the count, it had to be an integer, a whole number, right? In the case of the continuous variables, then we don't have such restriction, okay? For example, what's the height of an individual? Let's say if we are using a metric system, we're going to measure 5 different friends, right, or individuals, and record their heights in using meters, right? First one is 1 meter 73 centimeters, 1.82, 1.77, and so on, right? So you can see they are not integers, and they can take on any value, okay? Reaction time, right? How many seconds or how many minutes does it take to react to something? Or, for example, if let's say how much of a time in days or years does it take for someone to develop certain symptoms of a disease and so on? Or what's the IQ level of the individual? Again, there's no restriction of what kind of value they can take and so on. Okay. They are also synonym for an interval variable. Again, in some of the textbooks, you might read the name interval variable. Just think about it that it is the interval variable and continuous variables are the same. And continuous variables can also be negative, okay? For example, when you look into, well, how much the wealth, right? Well, if you have money in your bank account and no debt, then it's positive wealth, right? But then if you have some money and then lots of debt, then if your debt is more than the wealth or the savings you have in your bank account, then you are going to have the net as a negative number. Okay, so again, the continuous variables can also be negative, or the revenue by a firm, right? In any given quarter or a month, the firm might generate negative net revenue or negative profit, depending on how their operations are being handled. Okay. Now we come to the qualitative data. Okay. Remember, the quantitative data, they do have the natural scale of measurement, right? Like Fahrenheit, kilometers, and so on. In the case of qualitative data, they do not have a natural scale of measurement. Okay. They are usually used as independent variables or predictor variables in our equations, like the x variables, that contain values that indicate membership in one of several possible categories. Okay, for example, gender is a qualitative data, right? And gender, you can either be a male or female, right? For example, if you were using only binary version of classifying the gender. Or marital status, right? Someone can be married, single, divorced, widowed, and so on. Okay. So as you can see, neither gender nor marital status has a natural scale of measurement. Okay, like similar to the Fahrenheit for the weather, and so on, or the temperature. In the previous presentation, we talked about qualitative research and quantitative research, and we have indicated that the purpose of our discussion is the quantitative research. I just want to make sure that we don't confuse a couple of things, is that qualitative variables are integral part of quantitative research, okay? We can always quantify qualitative variables, as we will see in the next couple of minutes, okay? By the fact that, I just want to make sure that all of us are on the same page, that the fact that we have qualitative variables doesn't mean that we cannot conduct quantitative analysis, okay? In reality, you'll see a lot that, especially in healthcare, a very large number of variables are qualitative in nature, okay? So there are different types of qualitative variables, okay? Again, they are categorical variables, right? That are non-numerical forms that don't have any order criteria, okay? Or think about this as gender, right? Male, female. There's no order. Nobody says that male is better than the female or female is better than the male, okay? Or someone's marital status, single, married, separated, divorced, widow, right? Again, these are just unordered, unranked categories, right? Nobody says that one is or can claim that one is better than the other. Occupational field, right? Someone can be a clerk, an engineer, a lawyer, a politician, an economist, and so on and so on, right? So again, these are occupation. All we are trying to do is categorize individuals into certain occupational fields. Okay, and in order to, as you can see, all of these are qualitative variables, right? But in order for us to conduct quantitative analysis, we need to assign numeric values to them, right? For example, if we have a gender, right, male and female, we might say, well, people who say that they are male will be coded as a value 0, and people who say they are a female then will be coded with a value of 1. And then what we have is, from a text description, male, female, we go into numerics, 0 and 1. And that's how we code when we are trying to conduct a quantitative analysis. Again, one of the things to keep in mind is that within the categorical variables, again, the variables that fall into 2 or more categories, they can be ranked, or there might be an order within, and unranked. In the case so far, we have been talking about unranked. However, data can also be ranked. In other words, there is a certain order in which they can come. For example, in the case of the occupational field here, right, we have basically assigned numeric values from 0 to 3, for example, to clerk, engineer, lawyer, politician. If we change the order, right, in other words, we say we switch engineer with clerk, right, engineer takes on value of 0, clerk takes on value 1, and so on, then nothing is going to change other than simply an interpretation. In case of the ordered data, the order doesn't matter, okay, which one appears the first or which one appears after another one, okay. Some of the examples that you might have seen in the literature can be, let's say, if you read the financial part of the journals or the newspapers, the bond ratings, right? Bonds are rated from AAA all the way to pretty bad categories, right? So we already know that the AAA is better than BBB rating, right? So you can see how there's a ranking in there. For example, if we conduct taste tests, right? So we are asked to sample something and we rate them A, B, C, and D, right? Well, A is better than B, B is better than C, and so on. Opinion survey, we say, how much do you agree or disagree with a particular statement, right? Insurance coverage, none, part, or full, well, full is better than part is better than none, and so on. So you can see there is a nature or the ordering involved within those. So employment of individuals, right? We have people who are unemployed, some are part-time employed, then we have full-time employed. Again, there is an ordering, right? Test grades, right? Let's say you are tested, you get an outstanding grade, a good, a satisfactory, and the fail grade, right? Of course, outstanding is better than the good is better than satisfactory, and so on and so on. Or you go to the Olympics, you can win gold, silver, or bronze. Of course, gold is better than the other two, and so on. And finally, our health status, right? If we are asked, well, how do you feel? What's your current health status, right? You can say, oh, I got an excellent health. I have a good health. Or my health is fair, or it's very poor. Of course, excellent, being in an excellent health is better than being in a good, fair, or a poor health. Okay, so as you can see, these are the examples that tell us tell us about the nature of this categorical data that has ordering involved within, which is quite different than the one that we have talked earlier about. Okay. And we usually use numeric values again to assign to them. Okay, and, for example, take the anxiety, right? They might be rated on a scale from none to a severe anxiety that a person has, and we might use some numeric values to refer to them. We'll start with 0 for none, 1 for a mild, 2 for a moderate, and 3 for the severe. Okay, we can actually switch the way they start, right? We can assign 3 to none, 2 to mild, 1 to moderate, and 0 to severe, and everything will be fine. The only thing we need to keep in mind is that the direction, it doesn't matter if it goes up or goes down, as far as we keep it consistent that the ordering of the categories is progressing or is going down. Okay. So it is really becomes very important that we do realize whether or not our categorical variable is ordinal in nature or not, especially when it is a dependent variable. When we use this data as a independent variable, then it's different. However, when it's used as a dependent variable, that becomes a matter of which regression analysis to use. If the responses, for example, are coded as 0, 1, 2, 3, and 4, then in the linear, when we use a linear regression, as we'll see as we move into linear regression, then it will treat the difference between 4 and 3 the same as the difference between 3 and 2. Okay? Again, the difference between 4 and 3 is 1, right? And the difference between 3 and 2 is 1 as well, right? Or we can use the opinions on in surveys, right? For example, do you oppose, or how do you oppose or support a particular, let's say, a bill or a legislature, right? Well, like strongly oppose, neutral, support, strongly support, right? Again, the key is we can start from 0 or we can start with 1, doesn't matter. It just needs to be progressively increasing or progressively decreasing as we you cannot just mix and match over here because you need to keep the ranking order of the categories that we are trying to measure. Another thing to keep in mind is that even though the numeric difference might be the same, right? Between 0 and 1, it's 1. Between 3 and 4, it's 1 as well, right? However, even though this is a 1 unit change, it's not the same, okay? Because here, we are opposing, and here we are in support of something. Okay. Some jargon that we'll be using. The first one is a binary variable. Okay. Again, binary variable is a special case of a categorical variable in a sense that it's just binary. It takes on 2 categories. Like previously, we saw that, for example, these opinions on a statement takes on 5 different categories, right? Well, the binary variables are the ones that only have 2 potential values, okay? For example, after a surgery, a patient's health can improve and not improve, right? It's either there or there. You have completed your homework versus you failed to complete your homework, right? After a particular intervention, the person is either alive or dead, right? You either agree or disagree to something. You smoke or you do not smoke, right? You can either be here or there, right? So these are where there are only 2 possible states of a situation that we can describe. Also, another one is called a dummy variable. Again, the reason that I'm bringing this up is that as you are reading the literature, you are going to see all of them, and I want to make sure that we have a good foundation of how different types of variables or variations of them are called. Well, the dummy variables are, as the name suggests, they are like artificially created variables, okay? By recoding the categorical variables that have more than 2 categories into a different series of binary variables, okay? So if we have a variable that has k categories, okay, then we would record them in terms of k minus 1 dummy variables. And I'll explain why minus 1 in a second, okay? So the remaining one, the minus 1, will become our base or comparison reference group. Okay, let's look at an example. Let's say someone's marital status is originally measured or labeled as 1 equals to married, 2 equals to single, and 3 equals to divorced, widowed, or separated. So what we can do here is we can take this variable and we can redefine them in terms of k minus 1. In this case, they're like k is equal to 3, right? 1, 2, and 3, that's k. Okay, we can define in terms of the 2, right, which is k minus 1. Okay, our variable 1 will be equal to 1 if someone is single, that's this one, right over here, and 0 otherwise. And variable 2 will be equal to 1 if someone is divorced, widowed, or separated, and 0 otherwise. Okay. So instead of one variable, now we have two variables. And I'll explain why we might want to do this in a second, okay? So for the person in the first category, which is married, then both variable 1 and variable 2 are going to be 0. In the regression model, we are going to omit the married in order not to cause something called a collinearity between the data sets, okay? And the married is going to be used as a comparison group. So whatever we or beta value we generate for variable 1 is going to be comparison between the single and the married. The beta for variable 2 will be the comparison between people who are divorced, widowed, or separated, which is the third category, and someone who is married. Okay. So the reason that we might want to do it this way is that we might want to express them as a separate variables in the regression, even though based on how the statistical software works. The software that we are using, Stata, its latest version allow us to create our codes in a way where we don't have to take this step of separating the variable. There's a syntax that actually does for us, okay? And as we talk more about and see the illustrations in the next presentation, you'll see how it is done. But I just wanted to make sure that as you are reading the readings for accompanying this presentation, that you are well aware that why dummy variables are useful and how they are created, okay? There are some other types of variables as well that we'll briefly touch upon throughout the study, okay? One is called truncated variables, and the truncation happens when the sample data are drawn or from a subset, and the subset of the larger population, okay? For example, if we take a group of people that make between $25,000 and $50,000, okay? So we take basically the subset of the group, right? Now we truncate this the entire population, and we only sample people who are between $25,000 and $50,000 of annual income, for example. Okay, so it is important to recognize that our data has been truncated because we cannot make an inference about the whole population, and then also the regression approach is going to be different. Censoring is more common than truncation. Well, censoring has to do the way we are coding our variables. Think about that. We are asking someone, well, how much money do they earn, right? And then we are recording these numbers. And then in our data set, anyone that makes less than, let's say, poverty line, let's say $10,000, we record them as a single value, right? And then everybody else, whatever they report. So as you can see, that creates, that is, and as we'll talk more about this later on, when we talk about censoring regression, this will create an issue because for the censored part, which is poverty line and below, it takes on a single value, whereas for everything else is the true value, right? So if someone makes $5,000 or $9,000, they are going to be coded the same, right? So there you are grouping these people, but there's no grouping rest of the time. So that creates some issues, and we need to be aware while we are doing our regressions and use the one that actually corrects for this type of stuff. And then finally, we have the selection or sample selection that is very common in health and healthcare and rarely is actually acknowledged by the researchers. Think about this. Let's think about a physical activity, right? Exercise, for example, that people engage. If we are looking into determinants of physical activity among individuals, right, then we would survey them, right? We'll ask them questions about their physical activity. And then we are going to code in terms of how much have they engaged in physical activity, let's say exercise on a weekly basis, right? So most likely we'll have some zeros there, right? Well, some zeros are going to mean whether or not person participates in physical activity, right? If someone says, oh, I don't do exercise, well, you just code them as 0. The other one says, well, you know what, I am physically active, I do exercise, however, I did not exercise, I exercised 0 minutes last week because I was sick or I was traveling, whatever, right? So as you see, we are going to record 0 in either case, but these are not the same zeros, right? So we already know that in one case, the person is physically active, it simply did not exercise because he or she was traveling or was sick. In the other case, the person simply does not exercise at all. The person is not physically active, right? Even though both cases are coded as 0. So in these cases, there is a selection. First, we choose to exercise or not, and then we choose how much to exercise. So when we have data that comes from this type of an experiment or this type of a design, then it is important that our regression model acknowledges it and provides an estimates that are theoretically sound. So this is what we'll be doing throughout the semester, trying to look into our data, trying to recognize them, and then as we recognize better, then we are able to select the better approach. Okay. Then the last kind that we'll talk about is called the survival data. And again, this is going to be very relevant to individuals in the public health or healthcare field. Survival data are basically, these are the variables that come in the form of a duration or the time that has elapsed until a certain event occurs or since an event that has occurred. Okay. This is also called a duration analysis. Some of the examples will be, let's say, unemployment duration. Okay. What determines how much time you spend on unemployment, time spent on welfare, days until arrest after incarceration, quarters until a company files for bankruptcy, right? If we are trying to understand what are the determinants of bankruptcy filing and so on, or what determines the longevity of the firms that would not be filing for bankruptcy. In the medical field, the person goes through a treatment, and we are interested, well, what's the likelihood of someone that will survive longer, right? What determines how long people have been tobacco-free or alcohol-free, right? How long will it take for someone to be hospitalized, right, with a certain condition? Time to death, for example, right? Let's say someone goes through chemotherapy. What's the survival until someone actually dies, right? Okay, is it 1 month? Is it 1 year? 10 years, right? Or what determines when someone might be, or how long it takes from birth someone to be diagnosed with a cancer or diabetes or another disease, chronic disease, okay? So these are all valid questions that we are trying to answer, and again, we are trying to model them and analyze them. And it is really important to realize that, okay, so in this case, we're talking about the duration, right? The time that elapsed or time since a particular event has happened, okay? So let me give you a final example, and then we'll finish today's presentation. So again, this is going to be an example of how we are going to merge regression analysis into some of the questions that we have to answer as health professionals. Okay, let's look into modeling individual smoking behavior, right? So when we read the articles, when we read textbooks, the theory and so on, then cigarette smoking is explained by multiple factors. For example, people's socioeconomic status, right? Their education, income level, and so on. Their demographics, right? Age, gender, race, okay? Some behaviors affect smoking, for example, alcohol use. There's a literature that shows that if people are smokers smoke more when they are consuming alcohol, or people might smoke only when they are consuming alcohol socially. Some attitudes, right, or how we perceive smoking. If people think that it's okay to smoke around the kids, then there's more likely they are smoking, right? The peer influence or social norming, okay? For example, smoking used as a way to make more friends or belong to a certain group, and so on and so on. As you can see, smoking is influenced by multiple factors, right? So the question becomes, well, how can we study these relationships? In other words, how does income affect your smoking? How does your education affect the smoking? If you use alcohol, how much extra you smoke, and so on, right? So what we can do is, again, we go back into our basic regression model, right? Where, remember, it was written as y equals to beta 0 plus beta 1x plus epsilon, which is our error term, right? Remember here, we observed y, this is the smoking, x is our characteristic, for example, income. This was our B from the linear model, and this was our M, right? Okay. So we can look into smoking as a function of age, right? Then depending what your age is, right, your smoking is going to change. Let's say individuals, as you age, right, going from like 15 to, let's say, 25, with every single age, our smoking level is going to change. You start with a single cigarette, maybe you go to like 10 a day, 15 a day, and so on, right? Or it can be part of a function of an income, right? Is our smoking increasing or decreasing based on income? Well, empirical literature tells us that as we become richer, actually, we give up smoking. Okay, so there's a negative. So we should expect beta 1 to be actually negative. Or how our alcohol consumption affects our smoking, right? If I'm consuming more alcohol, am I likely to smoke more or not? Okay, so these are kind of different ways of expressing the relationship in a linear model, right? And this is called a simple regression model. I will talk about it next time as well. Simple because there's only one x variable, right? That's the x, this is the x, then this is the x in every single equation. Okay, so that's the name, hence the name simple. So through surveys, we are able to observe the smoking and the age of the individuals. All we need is to calculate the values of beta 0 and beta 1. Okay, and that's what our regression analysis will be aiming to do. We are going to calculate these values. Okay, the general form of the regression model, remember this one was the simple form, okay, where there's a one y, one dependent variable, and one independent variable. But we do know that in real life, there are there's more than one variable that affects our behaviors. For in terms of the smoking, it's not only my alcohol consumption, it's not only my gender that might differentiate smoking levels, but also it's everything else that we just read about, right? What defines, what contributes to our smoking or affects smoking rates, right? So in a general form, regression model is expressed as y is a function of x1, x2, and x3, and the relationship between y and x's are characterized as in the form of the equation y equals beta 0 plus beta 1 x1 plus beta 2 x2 and so on, all the way to beta k xk and the error term. Okay, these x1s can be the age, income, and so on. Okay, here again, y, remember always the left hand side of the equation in regression modeling is our dependent variable. X are our independent variables, plural. Beta I are our regression coefficients. In this case, beta 0 is the intercept, and the beta 1, beta 2, and beta 4k are respective slopes. And finally, epsilon is our error term. As we saw earlier graphically, error term again is the difference between the actual and predicted values. So depending what type of x we have, x variable, right? Remember the different data forms, right? Account data, continuous data, ordered data, on not ordered, right? Depending on the type of the x, right, it's going to determine the inference and interpretation of the beta. Okay, that's it. In other words, what's the impact of xk on y? However, the type of y, which is right over here, is y continuous. Is it binary, right? Binary, let's say 1 and 0. Yes, no. Do you smoke? I smoke. I don't smoke, right? So type of y is going to determine what kind of a regression method we are going to use to calculate or estimate the values of betas. Okay? So again, x determines how we interpret beta. Y determines how we calculate beta. Okay? In this course, what we are going to focus on primarily is we are going to learn and use different methodologies for different types of Y data. Of course, we'll talk about the interpretations as well, but our focus is going to be learn of these different methodologies, regression approaches that are typical depending upon how your Y is measured. Okay? So that's going to be the purpose of our regression. So we go back to the smoking example, right? In a general form, the smoking behavior is equal to beta 0, right? No matter what, some people might just have a baseline smoking, right? Beta 1 age, beta 2 income, beta 3 gender, beta 4 alcohol, and so on and so on. Okay, so again, our beta k is going to determine, and this is what we are going to learn in the next time. The beta k is going to determine the statistical significance, the direction, either negative or positive, up or down, and the magnitude of the income impact. In other words, the effect of these factors, let's say for beta 1, it will be what is the significance, what's the direction, magnitude of impact of age on our smoking, okay? But also we know that, remember, this was X, right? So this had to do with XI, right? Okay. So we also know that smoking can be defined in multiple ways, right? For example, depending what kind of data you calculate, your smoking can be a binary, right? Do you smoke or not, right? Yes, no, right? Or smoking can be measured in terms of how many days in the past month have you smoked, right? So it can vary between 0 and 30, right? As you can see, this is like number of days, right? Or it can be how much money do you spend on cigarette purchases during the last 30 days. In other words, your monthly expenditure on cigarette purchases, right? So it can be any number between 0 and the positive infinity, okay? You can see here it is binary. Over here we have count data, right? Because it's 0, 1, 2, 3. These are integers, right? It's either we smoked in the day or not. There is no 1.7, for example. And then we have continuous data right over here, which can be 0, it can be integer, it can be 3.7, 59, and so on. Okay. So as you can see, this is our y, right? So that's why what I was trying to say is that depending which one of these, A, B, or C, we are using, our estimation of beta or calculation of beta, the way we do it is going to be different. In case of a binary, there's one approach. In case of a count data, there's another approach. In case of a continuous data, there's a completely different approach. Okay? So what we are going to do in this class is we are going to learn how to identify, well, how is my y measured, and which one is the correct estimation approach for a particular case. Okay? And this table summarizes pretty much what we'll be doing. Okay? If our y is continuous, okay, then we are going to study about linear regression, or also called ordinary least squares. If our y is binary, then we are going to learn about logistic, logit, or probit regressions. If our y is categorical without any ranking, then we are dealing with a multinomial, logit, or probit regression. If there is a ranking categorical, ordered, then we are talking about the ordered logit or probit. If we have a count data, right? In other words, how many patients did you see? Well, we are looking into Poisson or negative binomial regression. Sensor data, truncated selection data. Then we have Tobit, truncated regression, Heckman selection models. And finally, there's the survival data that will be using the hazard regression or the Cox regression. Okay? As you see, even though all of them might be measuring smoking, but they are different. The way they are measured, the way they are coded, and hence we have different regression approaches that is going to be used for each one of them. Okay, so that's what our purpose is, to make sure that at the end of the class, when you walk out of it and you go to practice all of this and conduct research and analytics, then you are able to properly apply the right estimation methodologies in this regression analysis. Okay, so next time, what we'll do is we'll start talking about the simple linear regression, the linear models, okay, similar to what we have here on the top, the continuous data, okay. That's where we'll start, and then we'll start gradually to move on. We'll talk about the basics, what the simple linear regression is. We'll do examples. We'll do hypothesis testing. In other words, we heard a lot about the concept of statistical significance of the coefficients. we'll do that, and then we'll also learn how to make the proper interpretations. Also, next time, I'll talk about Stata. I'll provide an introduction to the Stata software. I'll share with you resources for Stata, and I'll do a very short demo of the Stata software. Okay. Again, it is really important that by the next time you do have access to Stata. Okay, and the information is provided in the course website. And please make sure that you have access and it is properly installed on your computers. And again, you don't need to know Stata to succeed. I'll be going through basically providing the basic introductions and also sharing with you the materials that are going to be used throughout. Again, thank you for listening. I hope this was informative. And if you have any questions, please